This is the third lecture on partial differential equation. Today we shall solve Laplace's equation in spherical polar coordinates using separation of variable technique. Before going to spherical polar coordinate system, we first like that Laplacian in any orthogonal curvilinear coordinate system where coordinates are u, v and w can be written as 1 by hu, hv, hw, which are the length elements. Then hu by hv del v plus del w, hu hv h divided by hw del w, where for spherical polar coordinate system u is equal to r, v is equal to theta, w is equal to phi, hu is equal to h, r is equal to 1, h v is equal to h theta is equal to r, and hw is equal to h phi is equal to r sin theta. So the Laplacian in r theta phi coordinate becomes 1 by r square sin theta del r of r square sin theta del theta plus this term del theta of this is r sin theta by r, so this is sin theta del theta plus del phi of 1 by sin theta del phi. This becomes one by r square. So this is the equation. Now the Laplace's equation in spherical Laplace's equation in r theta phi coordinates is written as phi is equal to 0, where Laplacian is given by this, and according to separation of variable technique we use phi of r theta phi is equal to capital R of r, big theta of theta, and big phi of phi, where capital R depends on smaller only, capital theta depends on theta only, and capital phi depends on phi only. We now use this trial answers into this equation, and remember that for Laplace's equation right hand side is 0, so we may neglect this part and work with this part and can set equal to 0. When this operator operates on this part, this del r differentiation is effective only on capital R, and capital phi and capital theta are to be treated as constant. So this equation, when we use this and this, becomes ddr of r square sin theta d capital R dr, and theta phi remains as it is. I am just for the sake of brevity is not writing the arguments. Then the second, this is the first part. So del r operates only on r, so dr, and these part are taken to be constant, so they are not differentiated. Now this term is del dd theta. Then we have sine theta d of vic theta of d theta Now coming to this part, this is 1 by sine theta, then d2 big phi d phi 2 r theta is equal to 0. Let me explain the step once again. I have since the right hand side in Laplace's equation is 0, we have ignored this part because this can be multiplied to the 0 on the right hand side, which is again 0. Now this wave function is being operated by this operator. When we come to this del r operates on capital R, while theta and phi are to be treated as constant. So this is this term. When the del theta operates on this wave on the with this function, then it operates only on capital theta. Capital R and capital Phi are to be treated as constant. This is this term. And finally, this term is this. Now, for non-trivial solution, this phi is not 0 or for all the values. So we divide this all the sides by r theta phi. For non-trivial solution, we have this part is 1 by r ddr of r square sine theta dr. We can take sine theta out. Then the second term, this is 1 by big theta dd theta of sine theta d theta. Then we have this term plus 1 by sine theta big theta d2 phi d phi 2 is equal to 0. We multiply all the sides by sine theta, so that this term becomes, there will be a sine theta term, and so this is sine square theta r ddr of r square dr plus sine theta by big theta and this term is 1 by phi d2 phi d phi 2, which we take on the other side, minus 1 by phi d2 phi d phi 2. Now the left hand side, right hand side is a function of phi only, while left hand side is independent of phi, and they are equal for all values. So this must be equal to some separation constant. We always consider separation constant to be alpha square. Right now we are not saying anything about this alpha. The resulting equation is, if we choose it alpha, the resulting equation is d2 phi d phi 2 plus alpha square phi is equal to 0. The solution is, whose solution is phi is of the form e to the power plus minus alpha phi, and we know that phi in spherical polar coordinate, if we represent any physical quantity in spherical polar coordinate, then it should have a periodicity with respect to phi with period 2 pi. So firstly, alpha has to be real quantity. So we put the restriction firstly alpha as real. Furthermore, the requirement is that phi of phi must be phi of phi plus 2 pi. If we change phi by phi plus 2 pi, we land up again on the same point in xy plane. So the wave function must have this property, and which leads to the fact that e to the power alpha must be an integer, and we generally call it by m. So this is the one information. So the separation constant is alpha, and finally we call it as m square, where m is an integer. Here the solution takes values both plus m and minus m, so we are not writing the solution as a to the power plus im phi plus b to the power minus im phi. Rather, we write the solution as e to the power im phi, where m is allowed to have positive as well as negative integral values inclusive of 0. This choice matches the solution with the quantum number already introduced in vector atom model, that is the magnetic quantum number. Later on we will see that m can be identified with the magnetic quantum number of an atomic electron. So with this information we come back to the remaining equation. So phi equation has been solved, and we finally conclude that phi solution depends on m, and it is a e to the power im phi. With this phi equation we are left with this equation. So I am just copying the relevant part. This is sine square theta r ddr of r square dr plus sine theta by theta dd theta of sine theta d theta is equal to m square. So this is the relation coupled differential equation involving r and theta. We want to decouple it. So what we do, we divide both the side by sine square theta. So the left hand side becomes r dependent only. So we write it 1 by r ddr of r square dr, and we write this on the other side. So this is become sine theta big theta dd theta of sine theta this with a minus sign because it has been taken on the other side, plus m square sine square theta Now you see the left hand side is a function of r only, while right hand side is a function of theta only. So these both the sides must be separately equal to some separation constant. We call the separation constant to be beta. Beta is the another separation constant. Here and right at this point we could say nothing about beta, as we introduced a separation constant alpha over here and argued that the periodicity demands that alpha has to be real. Sinusoidal solution of phi demands that alpha has to be real, and furthermore the periodicity of phi solution demands that alpha has to be an integer. Now, till now we could say nothing about beta, so we just introduce beta and demand nothing about the nature of beta right now. It will be obtained later on. Now we start with the theta equation. So theta part is this. So we write it as, we take this part on the other side. So the first term is d2 big theta d theta 2 plus, when you differentiate it, this is cos theta, and in the denominator we have, so it is cot theta dd theta plus beta minus m square sin square theta of big theta. We take this on this part on the other side, so beta is positive, this part is positive, and this part is negative. And when we differentiate this part, so we have sin theta on the numerator and as well as in the denominator, so this becomes d2 theta d theta 2. When we differentiate sin theta, this gives us cos theta, so cos theta by sin theta is cot theta, and we introduce u is equal to cos theta, so that dd theta becomes du d theta ddu is equal to minus sin theta ddu, which becomes minus 1 minus u square to the power of ddu. So here we have double derivative, so we must be d2 d theta 2, this is equivalent to dd theta operating on dd theta. So this is minus sign to a double minus sign cancels, so this is first part. When this operates on this, we have 1 minus u square d2u du2, and when this operates on this, it is half 1 minus u square to the power minus half and minus 2u. So this becomes 2 cancels out, and this minus half and this plus half cancels out, this is minus u ddu. So this is minus u ddu. So if we use this notation, then in terms of reduced variable u, this equation becomes 1 minus u square d2 theta du2 minus u d theta du And from the first derivative term, consider this part. Cot theta is cos theta, so u upon 1 minus u square square root. Then dd theta has to be replaced by ddu, which gives you minus 1 minus u square to the power half minus u square to the power half d theta du plus this term beta minus m square 1 minus u square theta is equal to 0. On simplification, this becomes 1 minus u square d2 big theta du2. This is minus u. Here it cancels with given minus u. So minus u d of big theta du plus beta minus m square 1 minus u square big theta is equal to 0. Here theta, big theta is treated as a function of u. With m is equal to 0, this equation reduces to 1 minus u square d2 theta d theta 2 minus twice u d theta du plus beta theta is equal to 0. This is an equation of the form 1 minus x square y double prime minus twice xy prime plus alpha y is equal gamma y is equal to 0. This is the Legendre differential equation. So this is our old friend Legendre differential equation, and this is known as associated Legendre differential equation. We know that the Legendre differential equation, the solution of Legendre differential equation is obtained in the form of infinite series, and the infinite series solution diverges at x is equal to plus minus 1. Here u is equal to plus minus 1 corresponds to z axis, u is equal to plus 1 corresponds to positive z axis, and u is equal to minus 1 corresponds to negative z axis. So in the system where z axis is included, or we want to find the solution of Laplace's equation on z axis, the infinite series solution is divergent, so it cannot represent any physical situation. So to have infinite solution on z axis, beta has to have a special value L into L plus 1, where L by convention is assumed to be non-negative integer. With this, the solution becomes this solution becomes PL of u, that is PL of cos theta. So the same nature is being carried over to associated Legendre differential equation. So beta has to have this value, this quantized value, so that the solution is finite even on z axis. And when we use this particular value of beta, and m has already been ascertained from the phi equation, the solution of this differential equation is known as associated log or polynomial, and this solution is phi of depends on two quantum numbers. Cos theta is written as ALM PLM of cos theta plus BLM QLM of cos theta. where this is known as PL. So well, so with beta is equal to L into L plus 1, with L belonging to integer greater than or equal to 0, the solution is known as associated logar polynomial. So the solution is given by cos theta. There is a where this is known as associated logar polynomial of first kind or associated logar polynomial. It is also known as associated logar function of first kind, and this is known as associated logar function of second kind. This is the finite polynomial solution, and this is the infinite series solution. As you might recall that even for integral values of beta, one of the solution of logar polynomial becomes an logar differential, because differential equation becomes a polynomial. For even values of L, the even series becomes a polynomial, and for odd values of L, the odd series becomes a polynomial. The other one in either case remains infinite series, which has divergence and called the Legendre function of second kind. It is the associated Legendre function of second kind with divergence at the origin, and this is the first kind Legendre function of first kind or Legendre polynomial. So we have ascertained the value of L also. So this is L into L plus 1. One further thing. This associated Legendre polynomial is related to Legendre polynomial, simple Legendre polynomial by a relation. Let me just state the current relation. PLM of x is related to D. You know that M could assume positive as well as negative values. So for example, as per vector atom model, for L is equal to 1, M can have values 0, plus 1 and minus 1. If we are interested to get PL is equal to 1, M is equal to minus 1, then we are to differentiate P1 once. That's why we have put the modular sign. So the meaning is that d1 dx1 of p1 of x. This is the meaning. And similarly, PL is equal to 1, M is equal to 1 is also obtained by this relation. Now recall that it is a polynomial of order 1. It is a order L. So if we differentiate it L times, we will get a constant. If we differentiate it more than L times, I will get 0. The solution will be trivial 1. So the maximum times that we can differentiate PL, still we get non-trivial solution, is that we can differentiate it L times. So which sets a restriction on the values of this. This must be less than or equal to L. So now we can match our result that for a given value of L, M can have values from -1, minus L, the restriction comes from the property of associated Legendre polynomial and of Legendre polynomial. Now we see that two of our known friends, that is the orbital angular quantum number and magnetic quantum number that were introduced in vector atom model, has appeared to us from the property of differential equation. The phi equation, the periodicity of any physical quantity in spherical polar coordinate with respect to change of phi by phi plus 2 pi states that M has to be integer, and the theta equation, the finiteness of theta equation on z-axis sets a restriction on beta, separation constant beta, which leads to the an integer L, which will later be identified as the orbital angular quantum number. When you will study the quantum theory of angular momentum, you will see that L is the orbital angular quantum number, the quantum number that was introduced in Bohr's theory. Now we are left with R equation. The R equation has yet to be solved. So the R equation is this. This is R square d2r dr2 plus twice r dr minus L into L plus 1, R is equal to 0. Now R is equal to 0 is a removable singular point of the removable singular point. So we opt the solution as capital of R is equal to summation over k is equal to 0 to infinity ck r to the power s plus k with c0 not equal to 0, Frobenius-Fuchs method. So when this is differentiated twice, the power will reduce by 2, which is being adjusted by this. Again, all the term will have a single power. So the relation is that s plus k into s plus k plus 1 minus L into L plus 1 r to the power s plus k is equal to 0. Initial equation. Initial equation, we collect the coefficient of r to the power s. So we get c0 s into s plus 1 minus L into L plus 1 is equal to 0. Since c0 is not equal to 0, this is 0, so s square minus L square plus s minus L is equal to 0, or s minus L into s plus L plus 1 is equal to 0, which gives you s is equal to L or minus L plus 1. Now you see this, we cannot construct any recurrence relation out of this, because the equation, all the terms in this equation has the same power of R. So knowing C0, we cannot go to construct C1 or C2 or anything else. So we conclude the solution is a single term solution. That is, the solution of R equation is, for a given L, the solution of R equation is C0 r to the power s plus the other root c0 prime r to the power second solution s2, that is, it is c0 r to the power L plus c0 prime r to the power minus L plus 1. And this solution, since this solution depends on depends on L, we call it the constant, we call it AL/BL. So we have obtained three different solutions of phi equation. Let me write once again the solution. In solving Laplace's equation in spherical polar coordinate, we use the separation of variable technique to set the solution as r theta phi is equal to r of r, big theta of theta, big phi of phi. Now this theta equation comes out to be dependent on m. This equation has found out to be dependent on Lm. This equation is found to depend on L. So the solution now becomes depends on Lm r theta phi. Now we write for r, we write AL r to the power L plus BL r to the power minus L plus 1. For this part we write ALM PLM of cos theta plus BLM QLM of cos theta e to the power Im phi. The constant associated with the phi part has been adjusted over here. So we are not introducing any new solution. This is a solution for a particular value of L and the corresponding values of M. So the most general solution is obtained as the linear superposition of all such solutions. So the best general solution is r theta phi is obtained as summation over L is equal to 0 to infinity for a given value of L. M ranges from minus L to plus L in steps of unity, and the solution is Lm r theta phi. So this is L is equal to 0 to infinity, M is equal to minus L to plus L. Then we have AL r to the power L, BL r to the power minus L plus 1. ALM PLM cos theta, PLM of cos theta, BLM QLM of cos theta to the power Im phi. Now special condition, this is the most general condition. If we have as r is equal to 0 is a part of the system, then we see that this term diverges at r is equal to 0. So if our system under consideration has r is equal to 0 part, then BL has to be 0. The situation may be like this. We are interested to find out the potential at an internal point. So for internal point, r is equal, if we set our origin over at the center of the sphere, then r is equal to 0 is a point. So for internal point, BL has to be 0. And in the external region, there is no restriction on BL, because in the external region, r ranges from A to infinity. You note that for L is equal to 0, this is a constant term, and there are situations where the electrostatic potential has R dependence. In that case, A0 and A1 may be non-zero, but the coefficient of R square, R cube and other higher terms diverges as R tends to 0. So in this region we see that AL with L greater than or equal to 2 has to be 0 in the external region. Now coming to this part, if we have z-axis as a point on the system, z-axis is included in the system, then this part has a divergence. So we said BLM is equal to 0, which is most common situation. This is the case. And so the associated Legendre function of second kind does not appear. Pardon me, we have written it in this part. So BLM becomes 0 when the z-axis is included, and which is the case in most of the situations. So we write the solution as L is equal to 0 to infinity, M is equal to minus L to plus L, and this constant is adjusted with this. So we write it as, it's a single constant will be adjusted, and we write it ALM r to the power L, BLM r to the power minus L plus 1, PLM cos theta e to the power Im phi, with B is equal to 0 when BLM is 0. Another simplification occurs when the system has phi independence. The solution of the physical quantity is independent of phi, in which case M is equal to 0, and this reduces to Legendre polynomial instead of associated Legendre polynomial. For azimuthal symmetric case, symmetric cases, the solution does not depend on phi, that is M is equal to 0, whence PLM reduces to simply a Legendre differential equation, and the solution in which case becomes L is equal to 0 to infinity, no need of introducing PL. This is AL r to the power L plus BL r to the power PL cos theta. Now let me just describe a situation about azimuthal symmetry. Let us consider a sphere, and we put a charge on at a point outside it, and we say the z-axis is the line joining the center of the sphere with the location of the point charge. If we consider different points on this strip, the different points are separated by just the different values of phi. As the charge has been chosen to lie on the z-axis, every point, if we have placed a charge q over here, and this is a dielectric sphere, then each point on the strip will have equal induced charge, or the induced charge density will be the same on every point. So such a situation, we see that the induced charge density and hence the potential does not depend on phi, and which we refer to as the azimuthal symmetric case, in which case the Laplace's equation becomes this. Another thing is that this part together, if we freeze the R part of the Laplace's equation, that is, if we want to solve Laplace's equation on the surface of a sphere, then R is constant, so del R part disappears, and the resulting equation has the solution this, provided that the z-axis is included, so BL 0. This is the solution of Laplace equation on the surface of a sphere, and has a special name y Lm of theta pi, called the spherical harmonics. This is the solution. Spherical harmonics are the solution of Laplace equation on the surface of a sphere. The spherical, name spherical is obvious because it is on the surface of a sphere, and harmonics is that these are the harmonic solutions. If we want to solve the Laplace's equation in cylindrical coordinate system, then we say if we freeze the z direction, then we get the solution on the circumference of a circle, and the corresponding solution is called the circular harmonics. With this theory part, we end our discussion today, and in the next class we shall apply the theory for the solution of few physically interesting electrostatic problems.